All right, but with a slight bit of manipulation, it will. All right, so I could rewrite this as x to the negative fourth dx. All right, we're going to later on in the unit, well actually in the next unit, develop a good understanding of where the funky s comes from. For now, it's just a symbol that means antiderivative or integrate. So we think of it as an operation or a command. Right? So when you were introduced to the concept of a square root, you didn't particularly care necessarily. I mean, I did, but not enough to voice my concern in class. Like, okay, so where did that little check house thingy come from? Like, not the need for it, but like that symbol. Like, why that? Yeah, so, but for me, I think of stupid things like that. Some people would not consider that to be stupid. I don't know. Everybody I've ever said that concern to has said, okay, listen, you got to find better things to do with your time's out. So, but it has concerned me, but I will say not enough to actually find the answer to that question. So, I'll offer it to you. Through the Remind app, as usual, the first person that gives me the history of the symbol for the square root will get a bonus point. All right. Oh, paying attention. The first person, yeah. All right, it's first come, first serve. All right, so it's the power rule, but in reverse. So I'm going to increase my exponent by 1. Making it x to the negative third. I'm going to divide by my new exponent. Now there's an understood coefficient of 1, so if I divide that by my new exponent of negative 3, it's going to become negative 1/3. I'm just going to tack the negative on the top just because that's how math works. Yeah, I mean, technically you can write it as 1 over negative 3. It just doesn't look as nice. What's the one thing I'm missing here? C. The plus c. All right, so what do we have here? 8 problems on this page. So if I gave you like these 8 problems on a quiz or a test, and you didn't write plus C in each case, you'd lose half a point in each instance. All right, so it's a total of 4 points that you're just throwing away for something very simple. All right. Historically, it's always happened to one person in every class. I'm hoping that by bringing it up repeatedly, I can get that down to 0. All right, so that's with permanent marker. You know what I should do is like I should like change my last name to like plus CANN. So like it'll just be right there and just see it all the time. Okay. Yeah, no, now it just sounds weird. Yeah.
It sounds like some kind of like entertainment service. TED Plus.
CAN is like everything you could ever want in media. Like I don't know. It's like I don't know. It's like a person who kind of got to email late in the game. You know, like, okay, so there's no TED cans anymore, so I guess I'll just do TED plus can, like, or underscore. Ooh, underscore.
Or just like, whenever you like write a whenever you like write C, like the letter C, just add a plus before it, like
just
in all instances.
Plus calculus everywhere.
No, just have a plus C and don't explain it until we get to this.
Like, why is it always like that?
No, it's so cool. Typo, there's no frozen. I thought you were right.
Excellent.
Now you just got to know to look for it. All right. Magnificent. So this one, number 2, it's a little funkier because it's got a lot of ingredients. Now, technically, we could think of this, and this is really where it starts to get a little weird, but it's not difficult in its weirdness. It's just weird. So it's the integral of the difference or sum between different functions. Technically, that's the same as the integral of each one of them, added and subtracted as appropriate. So in reality, we're looking at something like this. All right. Now, on a test, quiz, AP exam, you would not have to write it separately because in the next step, we would integrate and then put it all back together anyway. All right. So the antiderivative of 3 to the x would be what? Exactly. Technically a plus c, but we're going to leave that off for a minute. Antiderivative of e to the x. E to the x. Antiderivative of x to the third. One-fourth x to the fourth. Plus x to the e as an antiderivative. X to the e plus 1. It's a little trick question or attempt at a trick question. And then I'm going to put a plus c off at the end. All right. The reason I can do that is what we talked about yesterday, is that if you have a plus c for each part, if I take all those constants and add them together, what am I getting as a result? Just another constant, right? And we would denote that with a c. Right. In which case, if you had plus 4c, if they were exactly the same constant, it would be a constant multiplied by a constant, because 4 is itself a constant, the result of which would still be a constant. Right? So that's why we call c the absorbing constant, because it absorbs all other constants like a gravity will. I was watching Star Wars Resistance last night. They had gravity wells involved, so it's on my brain. Antiderivative of 5 cosine x. 5 sine x plus c. Now, number 4 takes on a different form. Find a general solution for a differential equation. Right? So instead of dr d theta equals, we want r equals. All right, solution is it's not the differential form or a differential equation. It's the function that preceded that. All right, so in order to do that, I would get it into differential form first. Dr equals pi d theta. Then I would take the antiderivative of both sides. Now, in front of the dr, we have an understood coefficient of 1. We'll integrate both sides. What's the antiderivative of 1? Well, the derivative of 1 would be 0. If we were dealing with y's and x's, it would be y, but here we're dealing with r's and thetas, so r. Normally I'd say plus c, but I'm just going to consolidate this c with the one that's on the right anyway, so I'm just going to leave it off. Antiderivative of pi. Well, that would be derivative. Pi x, so pi theta. All right, variables theta plus c. All right, that's the general solution. We haven't talked about particular solutions except to say that they exist. A particular solution would be the case where we actually determine what the c value is. All right, we're not there yet. That's something for tomorrow.
Did you want us to remind you the order of the square root symbol?
Yeah, send it on reminder. All right. Oh, by the way, does anybody know what kind of equation this is? Something from pre-calc. You may or may not have seen it. Something that has r's and thetas instead of x's and y's.
Oh,
Polar.
sir.
Polar. So there is a place for polar equations, polar coordinates in this. In the North Pole. That's where we keep them all. There's a warehouse up there we store them in. It's a little bit ahead of the game, but the reason why I throw in a problem like this is because I wanted you to understand that calculus can be applied in different coordinate systems. So not just x, y, but r's and thetas, right? I'm testing tonight in my Calc 3 class on the derivatives and antiderivatives, like a full-blown unit related to polar functions or polar graphs. And so, obviously, what does that mean for you? It means you're a little ways away from being exposed to that in its full, to its full potential. But, just understand that this is something that you could look at also. Rates of change associated with polar graphs, parametrics we looked at when we did the basketball activity. And we'll look at parametrics again before the course is over. But, there's different applications to this stuff that span beyond two-dimensional coordinate systems. Because, you think about the real world, I think 2 dimensions are a subset of everything else, but it's not the entirety of it. You look outside, you got length, width, and height, right? And then the passage of time to kick in a 4th dimension, and so on. All right. So between now and I guess Tuesday, you're going to want to tackle the remaining problems on this page. They require you to do a little simplifying first in some cases. But generally, all of the processes that we talked about can be applied to these 4 questions. All right, so we haven't learned anything like a reverse of the chain rule or product rule or quotient rule yet. So simple, basic antiderivative rules can be applied to any of these questions. All right, so between now and Tuesday, you're going to want to tackle these problems. All right. So as long as you never lose sight of the fact that you can apply any algebraic knowledge that you have in the attempt to simplify, the goal being to make your life easier, then things are going to work out well for you, I think. So for number 5 here, you have a sum or difference in the numerator of a fraction. So that tells me that I can split the fraction. Yeah, just rip the Band-Aid. That's it, yeah.
Just do it.
Yeah.
1 second of loudness is better than just...
Exactly. It's the same thing with like a soda can. Like, you just pop the top, or you for 45 seconds, like. So x to the second over x to the 4th becomes x to the negative second. X over x to the 4th becomes x to the negative 3rd, so 2x to the negative 3rd. And then 3x to the negative 4th, so minus dx. All right. And, it's across the board, no matter what level, AP Calc, regular Calc, college Calc, it doesn't matter. In the early goings, it's funky S, the funky S and the dx is really just representing boundaries, parentheses, kind of. Just telling us, take the antiderivative of the thing in between these 2 symbols. All right, but in the latter part of this unit and the next unit, it'll become very obvious why those symbols are what they are, to the point where maybe you'd want to go back to just being like, all right, I like the old way better, but it'll involve more meaning. But it comes back to the concept of differentials, right? The area under a curve. So anyway, reverse power rule. So increase the exponent by 1, divide by the new exponent. So we're looking at negative x to the negative 1st. Now, the next one, you can show the intermediate steps, but if you play it out in your mind, it might be a little bit easier. Because if I increase this by 1, I'll get a negative 2. Take that 2 and divide it by negative 2, it's going to become a negative 1. So negative x to the negative 2nd. All right. Increase the power of negative 4 by 1, you get negative 3. Negative 3 divided by that new power will become a positive 1. So plus x to the negative 3rd. And as long as you don't forget your plus c, you won't be throwing away the easy points. that being said, I have had students before that didn't know anything about antiderivatives whatsoever, except for the plus C. So their final answers would be nonsense plus C in the hopes of getting a passing grade. Well, I mean, they got something because I didn't take off for getting the plus C. So they got like a half point for each question for remembering the plus C. The problem was they lost the other 4.5 points for not knowing any other aspect of calculus. So, so yeah, very important in the sense that you don't want to throw away the little points, but obviously you need to know the big picture too. All right. So parentheses, they're not overly meaningful when you see them in an integral, because I mean, unless there's two expressions being multiplied, because the funky s and the dx are serving as de facto parentheses anyway. So they're telling us, again, take the antiderivative of the thing contained in between. And we learned in a previous problem that we don't have to write them as separate integrals. We don't have to write antiderivative of x squared dx plus antiderivative of secant squared dx just to integrate them both separately. We could just do it all on the fly. All right, so we're looking at 1/3 x cubed. That's the result of integrating the x squared. What, pray tell, is the antiderivative of secant squared? Tangent of x, right? All right, and then r plus c. All right. The first part, that's an action. You know, you're applying a rule, reverse of the power rule. The second part is just a fact. If you know your derivative rules, then that gives you a good leg up in knowing your antiderivative rules. Right? So if you know that the derivative of tangent is secant squared, then whenever you see a secant squared, you'll know what the antiderivative is. So one's kind of like a verb and the other's an adverb. Really. That's the extent of my grammar knowledge. So a rewrite on number 7, I'd write it as x to the 1/2 plus 1/2 x to the negative 1/2. You could write it other ways, I suppose. Maybe consider rationalizing the denominator. But if our goal is to get it into a power rule looking format, then this would be the way to go. All right, so increase the exponent by 1, becomes 3/2. Divide the understood coefficient of 1 by the new exponent, 3/2, it becomes 2/3. And you could always check by taking the derivative. So apply the power rule and make sure that when you do that, the result is x squared. All right, the next part, increase the exponent by 1, becomes x to the 1/2. But then if I divide the 1/2 by my new exponent, it's going to go to 1 anyway. So that's nice. A little plus c action there. And you're good to go. Now you can't always rely on the calculator because, as you know, calculator part of an exam, non-calculator part of an exam. You know, I don't always do that on my tests, but you know, there's some questions where you just can't use a calculator. But you know, on the AP, it'll be put the calculator away. You can't use it at all. But when you can use the calculator, you may consider checking the graphs of your original function, the integrand, the thing you're taking the antiderivative of, and what you think the antiderivative is to see if they check out. So just to, you know, I might as well refresh on that now, because as the integral questions get more challenging, this becomes more of a valuable resource. And you know, it's not delusional here. If you're on the calculator part of an exam and it's a multiple choice question, for example, maybe you can get the answer without doing the calculus. You know, I mean, it's guess and check of the highest order, but you know, it's still guess and check. But if you don't have any other means to get a solution to a problem, then what else are you going to do? I am in polar mode. I'm going to change that. Mode, function. All right, so remember in Y4 you want to have the derivative. So I don't want to put an antiderivative function in here. I'm still working with the derivative function. So math 8 x, y1, x. That'll plot the derivative of whatever I put in y1. All right, so this is just the reverse of what we were doing in the first semester. What I would put in y1 would be my answer. All right, so 2/3 x to the 3/2 plus x to the 1/2. You might just put a radical x there. Less keystrokes. The only thing you can't do is the plus c, but you know it's going to go away anyway, so it doesn't matter. The drawback to that issue is in the next lesson, when we actually figure out what the c is, there's really no way to check that using this feature. All right, so there's other ways to check it, but this would kind of fall flat. All right, so this is my what quote unquote original function, but this is what I think the antiderivative is. Its derivative will get graphed in y4, so I don't really need to see this. What I need to see is a comparison between what the calculator thinks the derivative is and what the test paper thinks the derivative is. All right, so the square root of x plus 1 over 2 root x. All right, because, again, if the integrand is the same as what the calculator thinks is the derivative of this, then we're going to be in good shape. There will be some domain considerations from time to time, because we do have, first off, it's a radical, but also it's a radical in a denominator. So the domain has to be restricted to only positive values of x. So in my window, I'll go, I don't want to start it at 0. Maybe I'll start it at like 0.1. I could go to 5. I'll go to 10. For the y values, I don't really care. So I'll just zoom fit that. Clear zoom 0. Oops. Clear zoom 0. I didn't bold one of them. I should have. Yours might still be set to bold in y4. I'll change it in a second. And now you know how to graph a check line. Useful applications of math. Yeah, I'm going to put bold on because I don't want to just have to take it on faith that it's plotting one graph on top of the other. We could go to the table. I mean, for me, it's less satisfying. Yeah, they're the same, cool. I know I'm right, but when I have that nice bold one tracing over the other one, it just feels nicer for me. I don't know. I'm getting weird in my old age. Ah, look at that. Just feels right. Yeah, it's climbing the mountain. It's like the Yodeler commercial. There's like a track that's got like a toy yodeler, and it goes up the mountain.
Oh yeah.
Yeah. And it's yodeling the whole time, which is of course what makes it entertaining. So we know we did it right, and that's really all we're after. The last one, this looks like it should be the reverse of some kind of chain rule, maybe product rule kind of thing, but it's actually just distributive property. 4t to the 4th minus 4t squared plus 1 dt, and then reverse of the power rule. So 4/5 t to the 5th minus 4/5 t to the 5th plus t plus c. All right. So there is a moral to the story here, and you'll find this once we start learning more complicated techniques of integration. Some of them are pretty juicy, and they require, I mean, there actually is, there's a concept called trigonometric integrals that you can actually use that technique for this particular problem. It's just, it would take the whole page. So the theme moving forward is going to be, don't work from the most recent stuff backwards, work from the beginning of the course to the end of the course. Look for the simplest way to attack a problem, and then go from there. Because let's say you thought it was just simple reverse power rule, and you thought wrong. Well, if that's the case, you only wasted like 20 seconds on the problem. If you think it's something way more complicated, you might waste 20 minutes on the problem where you only needed to apply 20 seconds worth of work. You know, that you kind of feel foolish after that, right? So think simply, right? And actually, I would even amend that to say, don't even think to the beginning of this course, think to the beginning of all of math. Like, go for the simplest, the very simplest way to get an answer. From multiple choice, yeah, go back to third grade, because for some of the multiple choice questions, especially when we get to area problems, area under a curve, for example, if you look at the figure, some of them, I mean, it'll be like a funky equation. You get into like polar graphs and things like that. Some of them look pretty nasty. Like I don't know, just off the top of my head, secant of theta equals, yeah, r equals secant of theta. It's a line. Right? It's a bound. If you bound within that line, you're going to get a rectangular area. Right? So once you figure out what the shape would be, if you're just looking for the area, well, why would you do integral calculus if you have a choice? You would just base times height and call it a day. Right? So you want to be looking for things like that. But it also involves some expertise in recognizing different types of functions, which is why we've been kind of hitting that pretty hard throughout the year. I think it's always seemed like a throwaway topic, where it's like, all right, well, what do you think this graph would look like? What do you think that one would look like? And your answer might be, well, whatever my calculator says it looks like, because I have a calculator, and it'll tell me what it looks like. But sometimes just being able to recognize it without the use of a calculator can get you where you need to go much quicker, right? Surprisingly. Now, okay, so in the next lesson, antiderivatives and initial conditions and particular solutions. This is basically what we were talking about, just now we want to find the value of C. In order to do that, they need to give us something. Right? They gave us the integral. They were nice. They didn't give it to us in differential form. They just flat out said, here's the integral. Now get to work. But then they gave us a condition. Right? So they told us that f of 2 is equal to 4. That's going to allow us to figure out the value of C. Right? So if I'm finding the antiderivative of this one, it's pretty easy because it's just reverse power rule again. We're talking x cubed minus x plus C. But that condition is what's going to allow us to figure out the value of C. So I know f of 2 will replace all of the x's with 2's. And the result of that computation should be a 4. All right, so this will give us a 6 plus C equals 4. Therefore, C is equal to negative 2. And so what we had initially was a general solution. I don't know why I opted to go script there. I can't write in script. And then f of x, which would be x cubed minus x minus 2, would be our particular solution. That's like so easy. And it's number 1. All right, I'm going to jazz it up a little bit with number 2, just with the notation. But even number 2 is not going to be difficult. It isn't until you get to applications where it starts getting a little dicey. All right. So g prime of x equals 6x squared would correspond to, because what we want to do here is take the antiderivative of both sides, but can't just magically include notation. So what I would actually write here, this might seem like I'm unnecessarily making this more complicated, but I promise I'm not doing it for that reason. I need to justify to you where the dx is going to magically appear from. All right, so that's what this next step is all about. So g prime of x, the lowercase g prime of x, would be the result of the derivative with respect to x of lowercase g of x. Now, if we went a step back from that, it would become uppercase, because the hierarchy is capital as the antiderivative, lowercase as the original function, and then the primes start getting into derivative territory. So d g of x dx is the same thing as g prime of x, right? So that's the same as 6x squared. In the next step, putting it into differential form, it would be d g of x is equal to 6x squared dx. At which point I would integrate inverse operations cancel each other out. Derivative and antiderivatives are inverse operations. Right? So that just goes to g of x. So g of x would be the same as 6x squared dx, or the antiderivative of 6x squared dx. All right. So that just seems like a lot of extra fluff to get you to the part where you probably already knew originally, oh, I'm just going to take the antiderivative. Right? But this is the notational understanding that distinguishes one from being a person that just follows steps and actually can internalize the procedure. All right, so it's kind of like next level stuff a little bit. All right, so 2x to the third plus c would be my g of x. Now they gave us a condition saying g of 0, which is telling us that each x is 0. That's going to be equal to -1. Now, if your independent variable is equal to 0, oftentimes, not always, but oftentimes, that means that whatever the result of the condition is, that's generally going to be your c value. But you mix in trig and log functions, 0 doesn't always yield what you think it yields, right? Because here, if you plug in a 0, it cancels out any term involving an x. But let's say, for example, if I had, instead of x to the third, I had e to the x. Plugging in a 0 is not going to zero it out. E to the 0th power is what? 1. So you can't always guarantee that, but it is something to be on the lookout for. All right, anyway, so I know my c value. My red equation there was my general solution. My particular solution, which is what I'm looking for, g of x, 2x to the third minus 1. And this is what I was talking about on the previous page with the calculator check. I can check this answer against my derivative, and it'll check out. But I could also check 2x to the third minus 7, 2x to the third plus 20, 2x to the third minus pi, and they're all going to check out because the constant's going to go to 0. What I'm getting at here is I could screw up this part of the process, and this answer on the calculator is still going to check out, and that's not a good thing, right? Because it's going to lead you to think that you're right when you're not, right? So the only thing I can tell you at this point is just be careful with your computation, right? Double check that. If you're in doubt and you want to actually use a calculator, you could use the check that I showed you, but also verify. Go into your table, verify that 0, -1 is a coordinate on this graph. All right. So if this equation checks out using the technique I showed earlier, and 0, -1 is in the table, then you're pretty confident that you didn't just butcher the whole thing. All right. Now, number three is my my favorite problem in the whole unit. All right, I like this one because this is the explanation behind a formula that you were just given, and you know, oftentimes you're given formulas, just know this formula and use it. Right? You don't really see where it came from. Honestly, you weren't really qualified to see where this formula came from because you didn't know integral calculus at that point. But the position function, if you remember that, I'll just jot it down on the side here. S of t, well, this is one variation of it, 1/2 at squared plus VOT plus SO, or whatever the physics variation of it is. You know, slightly different, VIs instead of VOs, right? So this formula comes from integral calculus, and we're actually going to discover kind of the origin stories. We're still working with particular values instead of general terms, but you'll get the idea. All right, they tell us that acceleration due to gravity is 32 feet per second. It's in the downward direction, so we'll know to make that negative. All right, so A of t is equal to negative 32 feet per second squared. All right, I'm going to go notation heavy again. All right, so A of t is the same as the derivative of v of t with respect to time. I'm going to leave the units in here. It's going to get a little messy, but I want to, at least this one time, show you something that kind of ends up being pretty cool, I think. All right, so get it into differential form. You'd have d v of t would be equal to negative 32 feet per second squared dt. At which point we would integrate. This is actually going to answer, hopefully, the question of where does the dt, the dx go when you integrate. It's a very exciting moment, I think. On the left-hand side, just having a v of t. Again, inverse operations cancel each other out. All right. Here on the right-hand side, we're integrating. We're finding the antiderivative of the negative 32, which is going to become negative 32 t plus c. All right, but let's just focus on the units there for a second. Feet per second squared, well, that's not the units for velocity. Okay? What we're actually doing, if we're looking at this as a measure of velocity, we write this in notation form, but it's really a product. It's negative 32 times 1 foot per second squared times dt. Now dt is a measure of time. So we're looking at feet per second squared multiplied by the units related to the passage of time, which would also be seconds. All right. So what units do you get as a result of multiplying feet per second squared by seconds? Feet per second. All right. So you don't have to show that every time. I just wanted to show it to you this one time so that you understand, well, it's not really going away. It's actually being multiplied by the units related to whatever function you're integrating. Okay? The problems that we were working with they were in a vacuum. They were unitless. I mean, that's not really true. They have units. We just didn't know or care about what they were. Right? But in this context, we do have units that we know and care about, so we can actually evaluate them. So when I take this dt and multiply it by feet per second squared, it actually gives us a meaningful answer, right? And an appropriate answer related to velocity. Anyway, ignoring units from now on, because I think I proved my point, we'd have v of t is equal to negative 32 t plus c. Before, because I'm looking for a position function, I have a velocity function. Before moving on, I need to flesh out what that c value is. Fortunately, they told us that we have an initial velocity of 64 feet per second. All right, just checking to see it's upward. So at time t equals 0, so v of 0 is equal to 64. All right. If I plug in the 0 for t, this part's going to cancel out, and so therefore c is going to be equal to 64. This is one of those examples where I was saying you don't really need to show the work because it's nice. It's at 0, so this number is your c value. All right. Now, notation-wise, v of t is the same as the derivative of position with respect to time. That's a differential equation. We put it in differential form. It's d s of t is equal to negative 32t plus 64 dt. Now, we don't have to show it, but just think about it for a second. If I were to take the units related to the negative 32t plus 64, which would be feet per second, and multiply it by the units related to the passage of time, feet per second times seconds, the result would be feet, which is the units of measure related to position. All right, so pretty cool stuff. Math cool. Physics cool, I guess. Math of physics cool, maybe. All right, so antiderivative, negative 16t squared plus 64t plus c. They gave us an initial height of 80 feet. So that's telling us that s of 0 is 80. If I plug in a 0 for t, each term containing a t will zero out, and that'll just give us c equal to 80. So s of t is equal to negative 16t squared plus 64t plus 80. All right, so this guy right here, oh, let me clean that up. This one right here, that appears to be 1/2 of the measure of acceleration. This one right here appears to be the initial velocity. And this one right here appears to be the initial height. Right? So anytime you were working with this formula, you were doing, at least indirectly, integral calculus. I mean, it's like freshman in high school. Pretty cool. Well, maybe even 8th grade. But that's the invention of the formula from scratch. Now, you do a process often enough, you start looking for shortcuts. So what happened was this process was used, and then they said, okay, well, we need to generalize this. So instead of working with gravity being 32, let's let gravity be g, or a if I want to keep it most general. Instead of giving a particular initial velocity, let's just call it VO. Right? Instead of an initial height, let's call it SO. And work with this in those general terms. And as you go through the process, what you end up with is this formula, but in its most general form, which is your standard position function. All right. So the follow-up question, that's not even calculus. When does it hit the ground? Well, I just kind of suppose I needed to ask you to do something with the formula after we came up with it. Negative 16t squared plus 64t plus 80 equal to 0. All right. It depends, calculator, no calculator. If it's calculator, then quadratic formula program sounds nice. makes sense in this context. I'm going to toss the -1, so therefore 5 seconds after launch? I don't know. I'll say launch. All right. If it's not, I mean, if you're not allowed to use a calculator for this, then, you know, GCF and go that route. But, you know, where you can, take advantage of these resources because you're allowed to use them, so why wouldn't you? I just graded all of my Calc 3 papers, and it's like feast or famine in that kind of environment. What I noticed was the students who got like 10s and 20s out of 100, aside from not knowing how to do any of the math, they didn't listen to any of my tips and strategies. And the people who got like high 90s and 100s, they listened to every single one of them. And it was very obvious where those strategies came into play, where I would show them how to create a polar graph on the calculator and analyze the graph. And as I'm looking out into the class, as I'm teaching this, I'm like, all right, you're getting that wrong, you're getting that wrong, you're getting that wrong, you're gonna be fine, because that person is like furiously taking notes, like looking up, okay, well, how did you get that? I'm not really sure. Go back a step. Okay, got it. And that all worked out well for them. The folks who were not interested, they looked at it as like, this is like fun fact of the day territory. It did not end well for them. And so, you know, like, it's just something simple. Like, maybe you find no interest whatsoever in something like this. But if I'm telling you, if I'm taking the time in class to tell you how to do it, especially the Zoom fitting part, you know it's something that's going to come up, you know, fairly frequently. And so, you know, just being able to, for the multiple choice questions, and sometimes I pick, I mean, you've seen the tests. I've selected questions where the analytic part of it will take forever if you had to do it by hand. But it only takes like a second and a half if you do it on your calculator. So if you're with me with the calculator approaches, you'll never have a problem with the test. Anyway, I've lectured long enough.